Hi everyone, let's look at the paper Approaching Deep Learning Through the Spectral Dynamics of Weights. This paper sheds light on the training dynamics of neural networks. They describe grokking, which is the phenomenon where neural networks overfit before generalizing uh, through the lens of the spectral dynamics of the weight matrices. They track a couple of metrics to explain the grokking phenomenon, the first being effective rank. For a matrix W with rank R, you can basically factorize it as U, sigma, and V transpose using SVD, and where sigma is the singular values. Normalizing the singular values and then looking into the entropy of this normalized singular value distribution will give you the effective rank. And normalizing the effective rank, basically dividing the effective rank by the rank of the matrix, allows you to compare this normalized effective rank across different weight matrices. So a high normalized effective rank basically means that the entropy is high, and which means that the singular value distribution is more uniform, or the matrix is high rank. Low normalized effective rank basically means that the distribution of singular values is more peaky, and there are few singular values which dominate, or the matrix is low rank. In this paper, they track how this effective rank changes as you continue to train your network. The other metric which they track is alignment between consecutive matrices. So again, with SVD, you get the left singular vectors in the U matrix and right singular vectors in V matrix. So you can consider the right singular vectors to represent the dominant input directions and the left singular vectors to represent the dominant output directions. And you can basically, at a particular training time t, write your matrices in terms of the left and the right singular vectors. So here you decompose Wi in terms of the singular vectors, and you take another matrix at the next layer, Wi plus 1, and then you decompose this in terms of the singular vectors. So now you can basically compare, or you can compute the similarity between the left singular vector from one layer, and you can, again, there are R singular vectors, so you can pick the jth left singular vector, and you can compute the similarity with the kth singular vector from another layer. And so if you try to think of it in terms of the input and output directions, basically, you are looking at the similarity between the dominant output direction from one layer and the dominant input direction from the next layer. That gives you this similarity metric. So again, this is going to be a matrix because you can have different values of j and k. A11 would denote the similarity between the dominant output direction from one layer with the dominant input direction from the next layer. A12 denotes a similarity between the dominant output direction from one layer with the second dominant input direction from the next layer. So when you have a high value of alignment, it basically means that the most important directions are preserved across layers. And they track in the paper the diagonal values of A. So you're comparing the dominant direction from one layer with the dominant input and output direction, and you're comparing the second dominant output direction with the second dominant input direction. And you can also get one single number representing this entire alignment between two matrices by taking the diagonal elements and by restricting your rank to just the first 10. They have some interesting results. So the first column here represents four different scenarios. The dataset which they use is a modular arithmetic dataset. So the first figure here has 30% of data, and it doesn't use any weight decay. So you can see that this doesn't generalize well. The validation error remains higher than the training error after 40,000 epochs. The second row basically uses 30% of the data and weight decay is 1. This is where you see grokking. You can see that the validation loss basically goes down after you continue training your network, even though initially your training loss is low, and the validation loss is high. And the third scenario, you can see they use 70% of the data with no weight decay, and they use the hyperparameters from another paper which basically describes about slingshot mechanism. And the fourth row, this particular figure uses 90% of the data and no weight decay. The second column basically tracks the evolution of the singular values. So you can see that in the grokking case, the interesting thing is that the top singular values basically they increase and then they decrease and then they almost stabilize after grokking. So you can say that the network almost groks around this 20,000 epoch mark, and you can see that the singular value basically stabilizes, and it's much lower than the peak value it had. And this phenomenon is just seen here, but not in the slingshot or the last row where you use 90% of the data. The third column basically looks into the effective rank, and the interesting thing here is the second row, which is corresponding to grokking, where you see that the effective rank basically decreases after grokking happens. So after 20,000, you can see that the heat map is basically darker, indicating lower values. So the effective rank is low, which means if you look at the singular value distribution, then that would be peaky, or fewer singular values would be dominating, or the matrix at this point would be low rank. But if you see the other cases, you can see that, so the y-axis here is the layer. And if you see the other three cases, you can see that some layers basically have a low rank solution right from the beginning, whereas some have high rank, high effective rank, um, and that does not change as training progresses. The fourth column basically looks at the alignment between the singular vectors. So you basically have R, the diagonal rank on the y-axis, and then you have the epoch here. So for the grokking case, you can see that initially the smaller singular vectors basically are more aligned, but then as you continue training, you can see that the top singular vectors become more aligned, and this continues through the end of training. But you don't see such a phenomenon in the first case where there's no grokking. You can see alignment happen across all the singular vectors. And in the third row as well, you kind of see this, but you don't see this alignment move from the lower singular vectors to the higher singular vectors. So these were some, and the way they look at these, they compute the alignment is by looking at the embedding layer and the first attention matrix. So these are pretty interesting results. And so by and large, like as the network learns to grok, it basically favors a low rank solution, and that's evident in row 2 of the results.